Let us take a few numerical problems on the topics that we have covered so far. So far we have covered an introduction to the signals. What are the different type of signals? We have seen continuous time signals, we have seen discrete time signals, and then we have seen some of the basic test signals under the continuous time category. So we are yet to see the basic signals under the discrete time signals category. So we will take up a few numerical problems now. Let me take the first problem. Let us try to solve integral of minus infinity to plus infinity e to the power of minus alpha t squared into delta t minus 10 t minus 10 dt. So let us try to solve this. Now we know that x of t, when it is multiplied by delta t, that is the impulse function. Now what we get is x naught or into delta t. That is, what has happened is there was a 0 here. Okay, so let us take the generic case rather than taking the specific case. So when you take the generic case, it is x of t into delta t minus t naught. Now in this case, what I got when this is multiplied, when x of t is multiplied by delta t minus t naught, this becomes x of t naught into delta t minus t naught. That is, the t naught gets substituted into t of x. So on the very similar, this is similar to x of t, and this one is delta t minus t naught. Now in this case, when you do a comparison between this and this, you find that t naught is equal to 10, which means what I have to do is I have to substitute, and x of t is equal to e to the power of minus alpha t squared. That means I have to substitute this 10 into t squared. So this integral becomes minus infinity to plus infinity e to the power of minus alpha into 10 squared into delta t minus 10 dt. Now this gets evaluated because this becomes constant. This term now becomes a constant, so I can take it out of the integration. Okay, and we know that this gets evaluated to 1. Okay, so this entire thing gets evaluated to 1. So the answer is e to the power of minus 100 alpha. This is the answer. So we'll take up the next problem. So the next problem is 0 to infinity t squared delta t minus 3. Now from the previous problem, we know that now it becomes very simple for us to evaluate. So this becomes integral 0 to infinity. So I have to put 3 in t here. So it becomes 3 squared t minus 3 dt. Now this becomes 9 into 0 to infinity and delta t minus 3 dt, and this becomes, the answer becomes 9. Okay, so let us take the next problem. Let us try to evaluate another problem, say 0 to 5 delta of t sine 2 pi t dt. Now very easy. Now this also becomes very simple. So this becomes all that I have to do is I have to substitute for d. So here the t naught is equal to, in this case the t naught is 0. So if I substitute t naught, which is 0 into sine 2 pi t, the t of sine 2 pi t, if I substitute the value of 0 into that, the sine 2 pi into 0 gets evaluated to 0, and the entire integral becomes 0. So it's very simple, it's not very difficult. Okay, let us take another example, which is something much different from what all we have seen so far. This e to the power of minus t delta t plus 3. Now here the impulse function is advanced, not delayed, so it is advanced by 3 seconds. So I can write this as minus infinity to plus infinity delta t minus of minus t. So now the t naught is minus 3. So if I substitute that into this, if you substitute minus 3 into e to the power of minus t, then this becomes, this entire integral gets evaluated to 3. So the answer is e to the power of 3. Let us take one more example. So let us evaluate this x of 2 minus t delta 3 minus t dt. Now here, before we actually solve this problem, let us try to understand some concepts. We know that when let us say we are having something like this, delta t minus t naught. Now this implies, if I want to represent this is your y-axis and this is your x-axis, and it is time axis, and since this is delta t minus t naught, what I have to do is I have to shift it by to a distance of t naught. Now what about this? What about this? T naught minus t. Now if you try to plot this, it is going to be again the same, it is going to be at the same place as it had been before. That is, if you see, it was here, and which means these two are equal. Okay, so let me go to the next take the next page to explain further on this. So it is minus infinity to plus infinity x 2 minus t. Instead of writing delta, I will write it as, because I have just now proved that delta 3 minus t is equal to delta t minus 3. Sorry, 3 minus t is equal to delta t minus 3. So which means I can replace delta 3 minus t by delta t minus 3. So now this becomes very simple. What all that I have to do is I have to substitute for t in x. So it becomes 2 minus 3 minus infinity to plus infinity delta t minus 3 dt. Now the answer is x minus 1. Okay. Right. Let us take one more example. Okay. Minus infinity to plus infinity e to the power minus t delta 2 minus t dt. Now we know that delta at minus b, I can write this as 1 by a delta t minus a by b, it should be b by a. So one of the properties of the impulse function, we can actually write it like this, and when you do that, when you apply it here, over here, this becomes minus infinity to plus infinity e to the power of minus t 1 by magnitude of 2 delta t minus 1. 2 by 2 it is, so it is 1. Okay. Now it is very simple to evaluate. So the answer you can very easily see that it is delta minus 1. So this is your answer for this problem. We'll take up the next problem. We'll try to take up a problem which is not so easy to it's a slightly complicated problem. Let us see that. Okay. Okay, let me take the last problem. Minus infinity to plus infinity, t to the power of 3 plus 4 delta 1 minus t dt. Now this from the previous exercise we know that it is t minus 1 minus infinity to plus infinity when you put it in brackets. So this the answer becomes 5. Okay. Okay. Now let us move to another topic, which is discrete time representation of discrete time signals. Now we've seen what is discrete time. We've seen what is discrete time signal. So we have to study. We have to see how it can be represented. What are the different ways it can be represented? Discrete time signal. So we know that discrete time signal is something like this. We have at discrete intervals of time there are samples. Okay. Maybe we can extend this. So let us call this is 1 and this is at 2, and this is the index number. So the axis is the index number, and we have 1, 2, 3, so on and so forth. Similarly, on the negative side also we can have some even in the origin we can have a sample. So this is called as a sequence. Okay. So this is a discrete time sequence. It's all another name given to discrete time signal. Now there are different ways to represent a discrete time signal. The one that I have just drawn is known as a graphical representation. So this is something like this is one of the representations that is done in order to represent more familiar method of a way of representing discrete time signals. So we have another representation which is very sequence representation. This is also very popularly used, sequence representation. So it is x of n is equal to, I can write it like this, 2, 3, 2, 0, then you can have 1.5. So usually usually you will find an arrow like this. If you see an arrow like this, it means that this particular sample is at the origin. Okay, so which means this is at -1. So this sample is at n is equal to -1. This one is at n is equal to 1, and this one n is equal to 2. This is at n is equal to 3, and this sample is at n is equal to 4. So it's a finite. This is actually a finite sequence. Okay, so it is not an infinite sequence, because the length, the duration is only finite in nature, because it exists only between n is equal to -1 and n is equal to 4. So between -1 and 4, the samples are defined. And other than when n is equal to when n is greater than 5 greater than 4, there are no samples. Again, when n is less than -1, again there are no samples. So this is a finite duration or finite sequence. Okay. So let us see. Let us try to understand another type of representation of the discrete time signals. So the next representation is the functional representation. So the functional representation is something like this: x of n is equal to one to say 0.5. Then I have 1.50. So 1 when n is equal to -1, n is equal to 0. 2 when n is equal to 0, n when n is equal to 1, n is equal to 2. Otherwise, this is also a finite duration sequence because it is having samples only between n is equal to -1 and n is equal to 2. So otherwise, it is having a value of 0. Okay, so this is known as a functional representation. Okay, so there's one more representation which is known as a tabular representation. Of all these representations, the most familiar popular is the graphical and the sequence representation. Okay, let us see how the tabular representation is done. X of n. So you have -1, 0, 1, 2, 3, so on and so forth. And the sample at n is equal to -1 is 1, 2, 2, so 0.5 and 1.5. Okay, we'll stop here. We will continue in the next lecture.